Today we are going to do section 5.1, which is on page 508 in your book. The first thing we're going to talk about is the so-called sigma notation. It's also called the summation. Okay. And to explain that, first let's consider this particular. I will turn this. Okay, this particular bunch of numbers. We are going to add numbers from 1 to 20 consecutively. That is, look at the bottom of the page. See the bunch of, is that clear enough? Yeah. See, we're going to add 1 plus 2 plus 3, etc. all the way up to 20. Your book is very patiently typed it all out, right? So that's what we're going to do. Now, to write all that out is you can write down, I am not going to write all that stuff out, okay? And we're going to use so-called sigma notation, which is a shorthand for expressing that big chain of numbers that we're about to add. The way we do it is to write numbers, to add numbers when you have 1 plus 2 plus all the way up to 20, increasing one at a time. The way we write with a sigma notation is like this. We are going to write down this thing. Okay, that's sigma or summation, whichever one you sounds better to you. And we will say I equals 1 goes from 1 to 20, and then we'll add up I. That means that, okay? That means for I goes from 1 to 20, we're going to sum up all of them one at a time, like this. So this one symbol will represent all 20 numbers typed out like your book does. And so, and then in general, we are going to, if you have a bunch of random numbers that to be added, we will write down like this. The summation as I goes from 1 to some n can be 5 or million, we don't care. And then each item will be called AI. In other words, it will be called A0. In this case, A0 will be 1, A1. A1 will be 1. We don't have any 0 yet. No zeros in this case. So A1, so I goes from 1 to n. So A1, 1, 1, 1. Okay, A1 is 1, A2 is 2, etc. And until all the way down to A20, in our case, is equal to 20. It can be equal to other stuff in other cases, right? Well, anything. The point is we have a bunch of variables or symbols that represent whatever number we want. And then the summation just means let's add all of them up, okay, from the first one to the last one. And the subscript here, when you say I, that's just each item. So this is one item. A1 represents 1 in our case. All right, so that's the meaning of the summation symbol. All right, so now that we know what the summation symbol does, let's look at the example. Now, example 5.1 on the next page, we have part A, okay? We have 3i when I equals 1, 2, 3, 4, 5. Well, then if so we have 3i. This is 3 to the power I. They want you to write down 3 to the power I where I equals to 1 to 5. All right? And we need to write down the whole sum. So what is the summation of, how do you write this? According to this summation way that we just learned, well, you write down the summation sign. Okay, we're going from 1 to 5. So you write down I equals to 1 goes to 5. And then what is each item? What is AI? AI is 3 to the power I in this case. And then they want you to add that up. So then if you add 3 plus 3 squared plus whatever all the way to 3 to the power 5th on your calculator, you will come up with some kind of answer, which I'm not going to pay attention to right now. Okay, you can look at that. And then part B is a similar situation. So then I will let you do part B for homework. All right. And we'll move on to the bottom of the page where we have certain rules of summation. The rules of summation is that if you have a constant in here, I'll write down the rules. Now, if you have a summation of some kind of a constant inside, if you just have summing a bunch of constants from I equals to 1 to say n, then you just, all it is you just have all the same, okay? All your AIs are identical. So you just keep adding until you have n of them. So then the answer is simply equal to n times your constant, right? Because yeah, there's no change. So that's rule number 1. Rule number 2 says that if you have a summation with where you have a constant times AI, okay, that is, there's a constant for each AI, where I again goes from 1 to n. You add all this stuff up, and then well, you can simply factor out the constant so that you just sum that up, sum just the AI themselves. I goes from 1 to n. That, of course, only applies if you have a constant for each I. Okay, if the constant is missing for some of the i's, then this does not work. It has to be on each I. All right. So next, the sum, that is, if you have, oops, oh no. Oops. My PDF suddenly flipped to the end of the book for no reason. And anyway, so we're back. And similarly, the other obvious rules is when you have the sum of two things, you know, AI, look at the bottom. When you have the sum of AI plus BI, that's just the sum of each individual one, and the same as minus. All right, so that's those are the basic rules of sigma notation. And there's one more. What does that say? Oh yeah, there's one last one that I should write down, which says that if you have your regular sum, this rule is also fairly obvious. 1 to n, okay, that your regular summation, and that will equal to the first part to and let's say m is some number in between. That is, m is between I equal to between 1. Let's say 1. Does this say 1? Yeah. Let's say this is 1. If m is a number between 1 and n, you know, somewhere in between, that equals that's the same as you adding up from the first one to the number m, and then AI, all right? And then you continue to add from n plus 1 to finally get to n. In other words, if you have 5 of them being added, right, you can, it's the same as adding the first 3 and then adding the last 2. So yes, that's pretty obvious, right? So but we should write it down, because sometimes when you see a lot of symbols and you stare and you forget all about what this is. So this rule will make it very clear. Okay, so I'm not going to talk about the proofs here, because I think the proof is quite obvious. And so we'll move on. We have certain rules. These are very neat rules, okay? And I'm not going to copy them down. I ask you because they're not going to be proven. And these rules are looking at the bottom of the page. Let's see. Okay, my camera is focusing. So you see there are several rules here. That is, if you have a sum of consecutive numbers, look at the first rule, 1 plus 2 plus 3, etc., all the way up to some n. There's a formula to add it all up. You don't have to do the addition by hand, you know, adding to what if n is a million. That will take you a while. You don't have to do that. In that particular case, there's a formula that can calculate it very quickly. The formula says E equals n times n plus 1 over 2. The formula is related to the area of the trapezoid. The area of the trapezoid is the base times the top plus bottom times the height over 2, and that's what the idea of this is. So that's how you can memorize this formula. In fact, is remember the area of the trapezoid. although it's not really that big a deal that you have to memorize this thing. You just look it up, okay? Just remember there is such a formula. If you have a sequence of neat numbers going one up at a time, then that's how you calculate the sum without actually doing each addition. Similarly, if you have a sequence of squares going one up at a time, and then there's another formula. And what's the third one? The third one is yeah, the third power. Same thing. There's some neat formula that will allow you to add it all up. The formulas are proved in by mathematical induction. You might or might not have proven this already in pre-calculus, but it's not important right now. Okay, we're not doing mathematical induction right now. We're just going to do this. We're just going to use these formulas, whether you remember them or not, but we're going to use them to solve some summation or sigma notation problems. Let's, as an example, let's look at example 5.2. Example 5.2 says that wants you to sum this stuff up. Okay, let's look at example 5.2. 5.2 says that they want you to sum this stuff. To sum up, what are we summing? I minus 3 squared. And for I going from 1 to 200, okay? Now we most definitely don't want to do this, punch this in the calculator and add it 200 times, right? That will take forever. So then what we're going to do is use the formulas that we just noticed. And how is that going to happen? What we're going to do is multiply that thing out, I guess. Yeah, that's what your book wants you to do. Okay, you're going to multiply this out, and then use the three formulas that we just learned about for summation of I and all those things. All right. So I will let you to do the details as homework. Let's look at part B. Part B is the same way. Okay, you have a summation of stuff to the power, and you use the formula to get it out. And it's also straightforward, so please do that as homework. The same with example 5.3. Please do that as homework. It's just a regular, straightforward application of the formula. So let's move on to approximating area. Now let's have a function, okay, f of x, and there is some area under it. Well, what I mean is that, take a look at this. See the blue part? You have a function. The function is the line on top, and what's the area under it? And you might wonder, why do I care about the area under it? Well, sometimes it's useful. So, and we're going to figure out what the area is. But the problem, of course, is this area isn't like any area that you've seen. And it's not a triangle or a circle or a rectangle that you know how to do the area of. It's just some random shape. At least one side is, right? The other sides are at least okay. But that one side is only a random shape. So how would we find the area? And here comes all the cute tricks of this section of how we're gonna pull off the difficult or impossible trick of finding the area under some random curve. Now to do that, first we need to know what a partition is. A partition basically means the definition is at the bottom, but basically what a partition means is we're gonna cut the area into slices. Yeah. Let's look at the next page, figure 5.3. So that's a random curve, and we're gonna slice the area into equal slices. Okay, and then what we're gonna do is calculate each slice. We're gonna calculate the area of the slice, and then we'll add it all up. That only approximates the area under the curve, of course. That's not the exact number, but it's something. Okay, at least we are having an approximation. So the slicing of it into equal parts is called a partition. Yeah. Anyway, so if you hear me say partition, you will know what that means. And then And then the area is approximated by, let's look at the next page, the left endpoint approximation. Okay, the left endpoint approximation means we're going to take the point, right. Maybe I should draw this thing. Yeah, I better draw this. Okay, so I'll reproduce this graph here. We are on page 513. All right, and I will draw this thing where we have a graph and where we are interested in the area underneath. Okay, right. So let's draw this. Some amount of area. We will. This is the partition. The partition is all equal slices of stuff. That doesn't look very equal, but it is. Okay, it's equal slices. Where we start at some point. This is x0. Okay, this is A, and that's B. That's not the origin, it's just how I drew it. Anyway, so A equals to x0, okay? And then and each partition, and this has n partitions, eventually B will be equal to x to the power xn, x subscript n. So then, and then we cut it, n is the number of partitions that we cut it into. In this case, n just equals to 5. All right, but it doesn't matter. N is a number of partitions we're going to cut it. And then how we calculating the area? The way we calculate the area, first we look at the left endpoint approximation, which means that we're going to use the left endpoint. So this is the area we try. The left endpoint is this one, okay? And then we'll calculate f of x. This f of x0. So this is f of x0. And then this little area would then be this section here. This section is called delta x. Okay, so the little area here, which I will shade it like this. So the little area, the small of the slice, I will write down slice. My little slice area is equal to f of x0. And that's that value here, times the delta x. Now remember that delta x is one variable, okay? It's not delta nx or nothing. It's delta x is one thing, like x or y or a or b, one variable, and it means this small distance. Delta means change. That's why we call that. So we have f of x0, which is that thing length, okay, times the delta x. That gives us a first slice. And then once we calculate the first slice, then we that's why it's called the left-handed endpoint approximation. We're calculating on this point, and then multiply, and we continue doing so. And the next slice we will calculate this one. Okay, that's f of x1, 1. And do the same thing. The next slice, f of x1 times delta x, and we continue doing so until we get to this last one, which and that will give us this last slice, okay? And that gives us an approximation that of what the area under the curve is. And so the left endpoint, ln, area of the left endpoint is you add all that stuff. Ln equals left, okay, equals to the summation of from I equals to 1 to n. You add up all these things all the way, f of x I minus 1 times delta x. The reason is I minus 1 is when I is 1, you start at 0, x0. So that so then the left hand is the very first point, and then but you go all the way only to x, the point before last, n minus 1. See, you don't need the last point because you're doing the left hand approximation. Similarly, if you look at the bottom, so once you multiply all this stuff up and each slice, okay, you multiply it patiently, and then you add it all up, and that gives you the entire area approximation only of this thing. And now, why did we use the left endpoint? There's no particular reason. We can also use the right endpoint and do a different approximation. Similarly, the right endpoint approximation, it would be equal to the summation of, if you look down a little bit, okay, is a similar formula, except the I get pushed 1 because you will do f of x just I, because you will do this one, okay, instead of the one before. So it's just f xi delta x. And that would be the right slicing. And so you calculate the right one, then is slightly different from the left one in the sense that for the same graph, we will have, see, I'm trying to draw the same graph. If you draw the right one, being that my example graph is going up, the right approximation will be higher, okay? It'll be like this, right? That's the whole thing. So it will come up. But that's only because this example I give happen to be increasing. If it's decreasing, then the opposite is true. But anyway, so that you can see the left and right endpoint, if the graph is increasing, then the left endpoint would have an underestimate, right? Because you're missing some spots. Whereas the right estimate will have an overestimate because you have stuff sticking out. But between for increasing functions, then between the left and right one, then you get the true answer. So you know your approximation is that the left endpoint is how much at least it will be, and then the right endpoint is how much at most it can be, if your function is increasing in that area. So having said that, so as you can see that you can see this coming. We're going to be doing a lot of grunt work, right? Because you have to find out f of x at all these points from 1 to n might be 100 or something, which luckily nowadays can be done by computer. But we're not going to do that much. We're mostly going to focus on what this means. Like, what is the concept? What's the idea here? How are we approximating the area? Well, we approximate it by slicing it real thin, and then add it up. Okay, once slice it, then you can see that the area is pretty close. So we're only doing approximation at this point. Okay, next page. Okay, so this graph then demonstrates what I mean by the difference between the left endpoint and the right endpoint. This is on the next page. As you can see, the left endpoint, being that the graph is increasing, using the left endpoint, all your areas estimate as under the graph, so you're missing. So your total is less than the actual area, whereas using the right endpoint, your total is more. So between the left and the right, you know where the area has to lie. All right. But if the graph is decreasing, then the opposite is true. And then let's see. All right. Now that we have described what it is, let's look at example 5.4, which you are giving some generic function f of x equal to x squared, and then you're supposed to calculate all the stuff, okay, and then crank it out and see what happens. Let's see. So please do this as homework, because let's see, did they even do the right endpoint? I guess they did. Okay, so please do example 5.4 as homework, because it gives you a feel of what happens when you do all this grunt work. Not much happens, but you should do it. Doing example 5.4 will give you a feel of how this is done rather than just watch it being done. And then let's look at the next thing. The next thing is, next thing we will talk about is what happens. The approximation seems a bit rough, right? However, the approximation gets better and better if you slice it more. Okay, the same graph, that if you slice it like a large number of times, as you can see, your approximation is looking better, right? You can barely see any waste that's over or under. So the smaller the slices get, the more accurate your area would be. So let's see the next concept we're going to talk about is the Riemann sums. The Riemann sum is defined as this particular summation, okay? Now, where f of x, the summation is when I goes from 1 to n. I am at page, where's the Riemann sums? Page 519. Page 519, 519. All right, Riemann sums. What is the Riemann sums? It's almost identical to this. The Riemann sums is summation from going from 1 to n, f of xi, okay, and then delta x, where xi is within that thing. That is, xi is somewhere in there. You say, well, where is it? And in fact, your book put a asterisk on the x. Well, that just means that x can be anywhere in your strip. Okay, each strip as you go from 1 to n. Okay, before we've been talking about whether it's the left endpoint or the right endpoint. Well, this doesn't matter. It's some endpoint in there. It could be left, right, middle. Doesn't matter. Okay, the point is pick a point in there. Any point in there will do, really, left or right, and you calculate by the delta x, and this thing is called the Riemann sum. Yeah, see, even your book says let x, the x subscript xi, let xi be anything within your little delta x, and wherever that is. You know, each one has one of them. Pick one from each strip. So then, why? Because we're trying to calculate the area, and the Riemann sum doesn't really care that much where it is inside. And then, all right. So basically, the Riemann sum is this thing, but in general, because this one it cares about whether it's the left or the right. Or the Riemann sum doesn't care. Just anything in there will do. Okay. And then now here's something that comes. So far, everything looks pretty good, right? And in fact, obvious almost. But this is not. Now, the next thing I'm going to say is not going to be so obvious. But watch it carefully. What happens is that now that this is a Riemann sum, we are going to say this. The area under the curve will be defined as, so here's our area, equals to the limit as n approaches infinity of the Riemann sum. Summation n equals to 1, what? I goes from 1 to infinity. What? This is an n. What? Yeah, n goes to infinity. I goes from 1 to n of this thing right here that we wrote. F of xi over that's an I, xi delta x. Now let's look at this thing. This is tremendously interesting. You know why? Because what it means is that as you slice this thing smaller, n goes to infinity, so you cut thinner and thinner slices, then your approximation gets better and better, and it will get to your area. Now, now isn't that neat? You know, you're imagining slicing it paper thin, and so that your area will come out exact. The problem is, of course, that is the limit of n goes to infinity. We have never seen this before, okay? Right now, your limit has running two variables. N is going to infinity, and I is going from 1 to n, which might sound puzzling at first, but you're going to get used to it. Okay, just by staring at it long enough. So as n goes to infinity, you imagine in this function, you're slicing that area more and more and more and more. Okay, just getting more and more sliced up. And so you have more and more. So let's say you have 1,000,000 of them. N is at 1,000,000. So you slice your area under the curve into 1,000,000 slices. So your delta x is extremely small, and you multiply and add it all up. And then you're getting very close to the area, is what this means. As n approaches infinity, this sum will eventually approach A, the area under the curve. Now you might think, Well, that's cute, but how would you calculate that, yeah, right? I mean, really, we have never done any limits like this, okay? And because what are you going to use? The L'Hopital's rule? Sorry, doesn't apply. Any other trick? No, not really. Nothing applies. But we're going to learn new tricks in this section to figure out how to calculate this summation. So it's very neat. Now let's look at the next page. All right, the upper and lower sums. Example 5.5. Now example 5.5 and then later 5.6 are still doing the upper and lower sums where you add stuff up in some kind of an interval. And so I will assign that as homework. Please do that as your homework to get a better feel for upper and lower sums. Okay, that's and that marks the end of this section, I guess. So for homework, please do page 223, homework section 5.1, problems number 1, 3, 5, 7, 9, 11, 13, 17, 25, and 27. And yeah, and when you're done with the homework, I want to talk about some of them. One of them exactly. Problem number 25. Okay, we are supposed to calculate L10 for some function. We in this particular problem, notice that we don't have to actually come up with the numbers. We just need to set up the problem so that in sigma notation specifically. So we are going to do that, I guess. Problem number 25. Okay, so we are doing problem number 25 on page 524. So problem number 25 says that f of x, we need L10, okay, for f of x equals to square root of 4 minus x squared. Oops. 4 minus x squared. 4 minus x squared on and we're adding the area from -2 to 2. So we're doing the left end point limit or whatever it's called. And so that's that. Now, whatever the function is, isn't actually that critical. So all we need to do is there's a function, it's doing its stuff, and we have to do the left end point where but to write down the summation, we have to remember this, okay? That is, we have 10 levels, right? So, and it's the left end point, which means it start at -2. The levels start at -2 and eventually end at 2, okay? So then, being that we're calculating the left end point, then I goes from 1 to 10, okay? I equals to 1, etc., all the way to 10, where such that when I equals to 1, then the first one, x1, is equal to -2. That's the first point of our cutting, okay? We're going to be cutting this thing, right? And then when I equals to 2, then x2 will be equals to what? Well, it's from -2 to 2, so the whole length is 4. And it will increase each time by 4 over 10. So it will be minus 1.6 because it's equal to 2 minus 4 over 10. Okay? And so it'll go down to 1.6. And in general, what is the relationship between I and x? It is a linear relationship. It goes down one at a time. The I increases one at a time, and this goes down by 4/10 by each item. So you know it's a linear relationship, that is a straight line. So we are going to use the point slope formula to calculate x, the xi's in terms of I. Now what that means is that we need to pull out a formula that satisfies these conditions. So using the point slope formula, we get x xi minus, we'll pick one of them, minus this minus 2, okay? I'm doing the point slope formula now, y2 minus y1 over x2 minus x1 equals to y minus y1 over x minus x1, that one. The same one that we've been doing this whole time. So we are going to do the point slope formula. So x minus negative 2 and then I minus 1, okay, that's the first pair of thing, equals to this one minus that, minus 1.6 minus negative 2 over 2 minus 1. I'm doing this because I need a formula that represents xi in terms of I, because then I need that in the answer, okay? Which is why I'm doing this. So when you crank this stuff out, then you get something like x equal to x of I equals to what do I have? xi equals to minus 2 when you finish all this stuff, plus 4 times I minus 1 over 10 when you get it all done. I will show you so that you can read the details if you want. Yeah. All right. But anyway, so that by the time you calculate all that, that is the representation. And so then you plug it back into the original deal. And what was our deal again? Our deal is that the L10 by definition is equals to the summation, okay, of I goes from 1 to 10, and then f of xi delta x. And here delta x is 4 over 10, right? Each slice is 4 over 10. So where delta x equals to 4 over 10, and then okay, that's good. And then xi equals to this stuff right here. So we'll put all that in. We'll take delta x in front because delta x is a constant. So we'll write it. So L10, the answer is 410 times summation of I goes from I goes from 1 to 10 f of xi. So you plug this thing into this. That is, you put xi in here in terms of x. You have 4 minus this thing squared. What is that thing? This stuff. Minus 2 plus 4 times I minus 1 over 10. 4 tenths. Okay. Now I have, and that's actually the answer. That's the answer at the back of the book. And you look at this and you think, well, why does it say 410? I don't know. The book like a fraction, I guess. I would have written it. Ended up with something slightly different with decimal points, which is fine. And you can do either one. But that's how the book likes it. The book's answer is missing the squared though. This thing right here. I think that's just a typo. I mean, after all, it says squared right here, right? So then it should be squared, and that makes sense. Without the squared, then the answer will be weird. But anyway, so remember to keep the square there because that's what the function says before, and that's your answer. That's how to do problem number 25, which is slightly different from the examples that we've done in this section. But the way the trick is just to come up with the linear relationship between xi and I itself. And then the answer will pop right out. And number 27 is very similar, so I will not go over that, but you pull the same trick. The biggest part is just do the point slope formula. Same thing you've done this whole time. All right, so that marks the end of this section.